Physics chapter 4 laws of motion. I'll be continuing from where I stopped yesterday. That was Newton's second law. In this part 2, I'll be starting from Newton's second law. Newton's second law of motion. I have completed with Newton's first law of motion yesterday. Now let's go with Newton's second law of motion. The first law refers to a simple case when the net external force on the body is zero. Okay, the second law of motion refers to the general situation when there is a net external force acting on the body. It relates the net external force to the acceleration of the body. Basically, the first law is inertia and it depicts places where the net external force on the body is zero. Then it can be in uniform motion or it can be in rest, at a state of rest. The tendency of a motion of a body to resist the change in its state, which can be in uniform motion or rest, is called as inertia. Now the second law, it's basically where we consider the second scenario where the object is not under net external force to be zero, where the net external force on the body is not zero. When real situations, most of the cases the net external force will not be zero. So in this net external force, we will relate this net external force to the acceleration of the body. Now let's see. Momentum. Momentum of a body is defined to be the product of its mass and velocity, and it is denoted by the letter P. P equals mass times velocity. Momentum is a body is defined to be the product of mass and velocity, and this momentum is denoted by P, and P equals mv. Momentum is very clearly a vector quantity. It has a direction. The following common experience indicate the importance of this quantity for considering the effect of force on motion. Basically, this is very important. We will see how. Suppose a lightweight vehicle, let's assume a small car, and a heavyweight vehicle, we can say a loaded truck, are parked on a horizontal road. Okay, we all know that a much greater force is needed to push the truck than the car to bring them to the same speed in the same time. Basically, we intuitively know that when there is a truck and when there is a car, or we can say a trolley, if it's not a car, if it's a trolley and a loaded truck, we know that we can push the trolley easily compared to the truck. Or for bringing them to the same speed, we need to apply much more force for the truck compared to the trolley or the small car. Similarly, a greater opposing force is needed to stop a heavier body than a light body in the same time if they are moving with the same speed. Basically, when a truck is moving forward, actually not a truck, let's assume a trolley is moving forward, like a trolley is moving forward, we go in front of it and we can stop it. But what if it's a loaded truck that is going at 20 meter per second or 20 kilometer per hour? Can you go in front of it and stop it? Of course not. Even for a car, it is not possible for humanly possible. It's not humanly possible. Meaning the force required to stop that moving truck or car is much greater than the force required to stop a trolley or a shopping cart. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone. The mass of the body is thus an important parameter that determines the effect of force on its motion. Basically, in the both cases, where the first case, a truck and a trolley or a shopping cart or a car, a small car, we see that the mass of the truck is much greater than the mass of the car or the trolley. And in case of the stone, where we throw a light stone or a light stone from the top of a building, or a ball we can say, and compare it to a normal stone, a large boulder, a person can easily stop a small ball. But what if it was a big boulder? He can't stop that. That is why mass of a body is thus an important parameter that determines the effect of force on its motion. It the force required to influence the or affect the motion of the body depends on the mass of the body as well. That is what they're saying here from both these examples. And speed is another important parameter to consider. A bullet fired by a gun can easily pierce through human tissue before it stops, resulting in casualty. The same bullet fired with moderate speed will not cause much damage. Basically, this one, the thing which is basically the mass of the body is important, and also the velocity of the body is also important, which we said here is speed. Basically, let's assume firing a bullet through a gun and taking a bullet in your hand and throwing it. We can obviously say which will deal more damage, you throwing the bullet with your hand or shooting it from a gun or a pistol. It will obviously the gun which deals more damage. So we can say velocity, it depends on the, why does that happen? When you throw and when you shoot from a gun, the mass of the bullet is same. What is changing? The speed is changing. The velocity of the uh, bullet is much higher in case if it is shot from a gun than thrown from a hand. So that is why the damage when we shoot through a gun is very much higher than when throwing with a hand. Thus, for a given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. Basically, force to stop the body, if it is, or affect the body, affect the motion of the body depends on the mass of the body as well as the speed of the body. This is in case if it is a moving object. If it is in case of rest, we consider other things. But for example, if you want to stop a moving body, it will depend on the mass of the body as well as the speed of the body. Taken together, the product of mass and velocity, that is momentum. It is evidently a relevant variable of motion. The greater the change in the momentum in a given time, the greater is the force that is needed to be applied. Basically, momentum is evidently a relevant variable of motion. Motion depends on momentum, and the greater the change in momentum in a given time, the greater is the force that needs to be applied. It needs to be either for stopping or increasing. A seasoned, next example, a seasoned cricket catcher, I mean not a cricket catcher, but a cricketer catches a cricket ball coming in with great speed far more easily than a novice who can hurt his hands in the act. Basically, if you see the difference between a novice player and a seasoned cricketer, where he's catching the cricket ball, which the cricket ball is coming from great speed, the cricketer can catch the ball more easier and more efficiently than a novice. This is the case. This is the catching scenario. Force not only depends on the change in momentum, but also how fast the change is brought. A seasoned cricketer draws in his hand during a catch, allowing greater time for the ball to stop and hence requires a smaller force. Okay, by doing this, by pulling the ball down after catching it as well, he is increasing the time taken for that ball to reduce in momentum. If the momentum depends on the time as well. If the momentum change is high in a small time, the force needed will also be high. But if the momentum change is great in a large time, the force required will be less. That is what, by doing this pulling motion, the cricketer is creating more time here. More time for the momentum change. The momentum is slowly decreasing here, but it's not decreasing in a 1 second or a instantaneously. It is decreasing due to his pulling motion. It is decreasing slowly, so the effect or the force applied, the force required to be applied, also reduce. One reason is that cricketer allows a longer time for his hands to stop the ball. As you may have noticed, he draws in the hands backward in the act of catching the ball. The novice, on the other hand, keeps his hand fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantaneously, and this will hurt. The conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about. Basically, we see three things. The the force applied to stop the motion is directly proportional to the mass. Higher the mass of the body, higher the force. Second, the bullet example, where higher the speed of the body, higher the force we need to apply to stop the motion. And the third here, the time taken. The greater the time taken for the change in momentum, the lower the force required. The same change in momentum brought about in a shorter time needs a greater applied force. In short, the greater the rate of change of momentum, the greater is the force. The rate of change of momentum is basically force. Force basically is directly proportional to mass, directly proportional to velocity, inversely proportional to time. Higher the time gap, higher the time interval, lower the force required. Okay, next. Observations confirm that the product of mass and velocity, that is momentum, is basic to the effects of force on motion. Suppose a fixed force is applied for certain interval of time on two bodies of two different masses. Initially, at rest, the lighter body picks up a greater speed than the heavier body. However, at the end of the time interval, observations show that each body acquires the same momentum. Basically, we know that the product of mass and velocity is momentum, and this is the basic effect of force on motion. Basically, when we apply a force, the body will gain momentum. Okay, let's assume scenario where a fixed force, maybe 10 Newton of force, is applied for a certain interval of time on two bodies. One is a light body and the other is a heavy body, let's assume. We know that when we push a lighter body, it will gain faster speed. But when we push a heavier body, it will not gain much speed. So we can say the lighter body is faster than the heavier body when we are applying same forces. But studies show that the momentum gained by both of them, both the bodies, both the light and the heavy body, P light equals P heavy. Both the momentums will be equal. Why so is because momentum equals mass into velocity. When mass is less, velocity will be more. This is what we saw here. When we push a light trolley with 10 Newton of force, it will go much faster than a heavy truck, which is, or not a truck, let's assume a loaded trolley, a filled shopping cart basically. When we push a heavy trolley or a loaded trolley, then it will go when P equals mass is more, then velocity will be less. So based on this, we can say when same force is applied, when same force is applied on two bodies, no matter the mass of the body, the final momentum of the body will be same. That is what they're saying. Thus, the same force for the same, yes, time is also basically something we should consider. For the same time causes the same change in momentum for different bodies. This is a crucial clue to the second law of motion. In the preceding observations, the vector character of momentum has not been evident. We know that momentum is a vector quantity. It's obviously is a vector quantity, but it has not been evident so far. Now let's see. In the example so far, momentum and change in momentum both have the same direction. Okay, but this is not always the case. Suppose a stone is rotated with uniform motion in a horizontal plane by means of a string. This is the diagram. Basically, you are rotating the stone using a string. Force is necessary for changing the direction of momentum. Even if its magnitude is constant, we can feel this while rotating a stone in a horizontal circle with uniform speed by means of a string. Basically, even though it is going in circular motion, the velocity or the momentum of um, the stone remains constant, but we know it's a vector quantity, velocity, momentum. So the direction keeps changing in a circular motion here. So we need to apply force to change the direction. Okay, suppose a stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed. Basically, the magnitude of momentum is constant, but its direction changes. The direction keeps changing. A force is needed to cause this change in momentum vector. Basically, force is needed to cause this change in the momentum vector. That is the direction change. This force is provided by our hand through the string. Our hand will provide that force. Experience suggests that our hand needs to exert a greater force if the stone is rotated at higher speed or in a circle of smaller radius or both. Basically, we need to apply greater force if the stone is, if we want to spin the stone in greater speeds, higher velocity, or in case of when the string is kind of short in length. This corresponds to greater acceleration or equivalently a greater rate of change in momentum vector. This suggests that the greater the rate of change in momentum vector, the greater is the force applied. Basically, this when we need to apply more force when the stone is spinning with faster speed and when the radius of the string is less, this corresponds that the string the stone is gaining a larger or greater acceleration, and equivalently same we can define greater acceleration as a greater rate of change in momentum vector. This suggests that the greater the rate of change in the momentum vector, the greater is the force applied. Higher the change in momentum vector, higher the force we apply. These qualitative observations lead to the second law of motion expressed by Newton as follows. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Let's read that again. The rate of change of momentum, okay, of a body, and this rate of change of momentum is directly proportional to the force applied and takes place in the direction in which the force acts. As we know that force is the one that is inducing the direction of the velocity, as velocity keeps changing. Because of that reason, the rate of change of momentum is directly proportional to the applied force, and the momentum will always be in the direction of the force, the direction of the force which acts. Thus, if under action of force F for time interval delta t, the velocity of a body mass m changes from v to v plus delta v, that is its initial momentum, P equals mv changes by delta P equals m delta v according to the second law. Basically, the momentum is mass times velocity, but the change in momentum is mass times change in velocity. That is the according to second law. Force is directly proportional to momentum, change in momentum, that is, and force is inversely proportional to change in time. Higher the time interval, lower the force need to be applied. So we introduce a constant here, K delta P, proportionality constant K, F equals K delta P by delta T, where K is a constant of proportionality. Taking the limit delta T to be 0, the term delta P delta by delta T becomes the derivative or differential coefficient of T with respect to T, denoted by dP by dt. Basically, this is in case of large time intervals or large changes where we take dP by dt. It is the when they say delta t is reached, it tends to 0, it means that it is we are calculating instantaneous. Force equals k dP by dt for a body. A body normally we take mass to be constant. We know that dP by dt is the formula, and we know that P equals mass by volume, I mean not volume, velocity. We know that normally a body's mass is constant. As conservation of mass theory, mass can neither be created nor be destroyed. Mass will come out of the differential equation. dV by dt, we know it is acceleration. So finally, the famous equation of force equals mass into acceleration is thus created. The extremely popular force equal mass into acceleration. The second law can also be written as force equal kma, where k equals 1, which shows that the force is proportional to the product of mass m acceleration a. The unit force has not been defined so far. In fact, we use equation 4.4 to find the unit force. We therefore have the liberty to choose any constant value for k. For simplicity, we choose k equals 1. Basically, the unit of force, one unit of force has not been defined in terms of force actually. In terms of force, we didn't define force. That's actually it is. We didn't define force in terms of like unit force. But we for defining force or unit force, we use this equation, that is F equals mass times acceleration. We say the force is then the unit of force is Newton, and it is actually kg meter per second square. When we accelerate a body of mass 1 kg to 1 meter per second square, that is called as 1 Newton of work, not work, force applied. Force equals dP by dt, which is equals to mass times acceleration. In SI unit of force is 1, that causes an acceleration of 1 meter per second square to a mass of 1 kg. That is defining the force unit actually. This unit is known as a Newton. 1 Newton equals 1 kg per meter, 1 kg meter per second square. Let us note at this stage some important points about the second law. Important points about the second law are, in the second law, force equals 0 implies acceleration equals 0. The second law is obviously consistent with the first law. When we know that in the first law, inertia, where the net force equals 0, the acceleration of the body will always be 0 at net force equals 0. This is what happens. Then the body attains a state of uniform motion or complete rest. And in case of the second law, here as well, when the force is 0, it implies that A equals 0. It's not saying like the second law is different from the first law. It is actually the same thing, because we are in this universe, and in this universe, whatever works, they work coexistently. When force is 0, acceleration here as well, when net force is 0, acceleration is also 0. The second law is obviously consistent with the first law. That is what they mean by that. And the second point, the second law of motion is a vector law. The second law of motion is a vector law. It is equivalent to 3 equations, one for each component for the vectors. Basically, since it's a vector law, it has a direction. And we know that our world is a three-dimensional world where we have 3 axes here, 3 axes of x, y, and z. So we define force in all these directions, where momentum is also defined in all 3 directions, where force in x direction equals dpx direction by dt, which is also written as m mass of the body times acceleration in the x direction. Same for y axis, same for z axis. This means that if a force is not parallel to the velocity of the body, a force is not parallel to the velocity of the body but makes some angle with it, it changes only by the component of the velocity acting along the direction of the force. Basically, when this is a body, let's assume, when force is acting like this, actually let's assume it's not acting like this. Let's assume force is acting like this, and it's making a angle theta here. If the force is not parallel, here if we see this is the velocity vector, let's assume, here if we see this is not really parallel, it is making an angle like this. Here it is 180 minus theta, but make some angle with it. It changes only the component of velocity along the direction of force. Basically, when force is acting like this, force can be resoluted into 2 vectors. If it is like this, it can be resoluted into this vector and this vector. Only this vector of force will affect the velocity. That is what they mean. As this direction, it's going into the ground, so it doesn't really matter. Okay, let's continue. The component of velocity normal to the force remains unchanged. It only changes by the velocity along the direction of the force. The component of velocity normal to the force, basically normal means perpendicular to the force, remains unchanged. If basically if a body is moving in this direction, let's assume it has a velocity vector like this, it's a straight line, but let's assume the force is acting like this. If the force is acting like this, then the velocity here, which is acting in this direction, and this force here acting in this direction, there is a 90-degree angle formed here. In such a case, this velocity remains unchanged. The body will continue to move in this direction. It will experience a force like this, and a new velocity this side will be created, and it will move like this as well. But that is secondary, as we can say this velocity component, when this angle is 90-degree, doesn't change. This velocity will remain constant. But you might be confused, as that is not what is happening in reality. When we move a toy car, but when we keep something on that toy car, some kind of a weight on that toy car, without weight, the car will move faster or longer distance, but with weight, the car will move lower distance. If it is not affecting the velocity, the downward force, then why will the car, which is under the force, will move lesser distance when compared to a car which is not under any kind of weight? We will see that as we continue to read the chapter. For example, in the motion of a projectile under the vertical gravitational force, the horizontal component of velocity remains unchanged. This we saw in the before motion, the trajectory of a projectile, where we have two sine theta and cos theta components. But when we consider the horizontal component, the horizontal component will remain unchanged when there is no air resistance or such. It will remain continuing like that. Only the vertical component, which is influenced by the gravitational force, will change. The third point is the second law of motion given by equation 4.y. 4.y is force equals dp by dt, which is equals to mass into acceleration. This equation is applicable to a single point particle. This kind of law is only applicable for a single point particle, a point particle. The force F in the law stands for the net external force on the particle, and A stands for the acceleration of the particle. Basically, F in the law, F equals mass into acceleration. F is the force experienced, net external force experienced by the particle, and A stands for acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body, or even more generally to a system of particles. Basically, the law in the same form, this law only will apply to a rigid body and even a system of particles. When we are referring to a point charge, not point charge, a point particle, F is the total external force acting on that single particle. But when we take, this will also work, this law will also work even for a rigid body or a system of particles. In case of the second case, where we take a system of particles, the same equations, force equals mass into acceleration, in that case, force refers to the total external force. A point to be remembered is that we are talking about external force here, that is acting on the system, and A refers to a total acceleration of the system as a whole. We are not talking about individual particles of the system, we are talking about the whole system. More precisely, A is the acceleration of the center of mass of the system, about which we just study in detail in the chapter 6. Basically, we can say the force here in the first case refers to in the first case where it's a point particle, we can say the force in the equation force equals mass into acceleration. Force refers to the net external force acting on that point particle, and acceleration is the total acceleration of the point particle. And in case of the second case, where we consider a rigid body or a system of particles, in this case we consider force to be the total external force acting on the body, and acceleration to be the acceleration of the whole system of particles, or the center of mass of the system of particles. any internal forces in the system are not included in the force. Basically, as it's a system of particles, there are many internal forces, energies inside the system, but these forces are not included in the force. That is the force in the F equals m into A equation. That force and the acceleration at instant is determined by the force at that instant. The moment after a stone is dropped out of an accelerated train, it has no horizontal acceleration or force. If air resistance is neglected, the stone carries no memory of its acceleration with the train a moment ago. Basically, the acceleration of a body is is depending on the force acting on that body at that instant. At one instant, at the first instant, the train was inside the, not the train, the stone was inside the train at this lady's hand, or at that man's hand, or whoever it is, at that person's hand. At that time, when the train was accelerating, the stone was also accelerating. But let's assume that person threw the stone out. At the instant the stone leaves the hand of that person, where it is in the air, or let's assume in a vacuum because we neglect air resistance. In such a case, at that instant itself, when the stone left the person's hand, it is not experiencing any kind of force. When it is in the hands, when it's in the man's or the person's hand, the the person was accelerating with the train, the stone was also accelerating. But when it left the person's hand, it was in free space. There was no force acting on it. And we can say the acceleration also on that stone is also zero. It will not remember like I was accelerating with the person, so I should accelerate now as well. There is no such thing. It will it will have no memory of its acceleration. At that time, the acceleration will be zero. Now, the second law of motion is local wait. I think I missed things, right? No, I didn't miss it. Okay, fine. The second law of motion is local relation, which means that force F at point in space, location of the particle at certain instant of time is related to A at that point at that instant. Basically, force at a point in space, that is location of the particle at a certain instant of time, is related to acceleration at that point at that instant. Basically, a simpler terms of saying that is acceleration here and now is determined by the force here and now. Only when there is a force, only when there is an acceleration. And this force, the instant this force is zero, the acceleration also will become zero. There is no delay in that. The instant the force will become zero, acceleration also becomes zero. Not by any history of the motion of the particle. Basically, there will be no history that I was accelerating when there was a few seconds ago. Now also I will accelerate. There is no such thing like that. Example, a bullet of mass 0.04 kg moving with a speed of 90 meter per second enters a heavy wooden block and is stopped after a distance of 60 centimeter. What is the resistive force exerted by the block on the bullet? Let's see how they solve it here. Basically, the retardation is A of the bullet. We find the acceleration using the Newton's equations, or the motion equation, the three motion equations. We find acceleration, which we get to be around minus 6,750. It is minus because it is a retardation and not acceleration. And we know that mass times acceleration is basically force. So we multiply with the mass of the bullet, which is 0.04 kg or 4 grams. When we do that, we will get the force to be around 270 Newton. The actual resistive force, and therefore retardation of bullet. The retarding force by the second law of motion is the actual resistive force, and therefore The retardation of the bullet may not be uniform. The answer therefore only indicates the average resistive force. The retardation of A of the bullet is assumed to be constant. The retarding force by the second law of motion is is the actual isn't the actual. I think it is not the actual resistive force, and therefore the retardation of the bullet may not be uniform. This answer we got, this 270 Newton, is actually only the average resistive force. The motion of a particle of mass m is described by ut plus 1 by 2 gt square. Basically, this is equation here. This is the one here given. This equation is the one they gave here as well. Find the motion of a particle mass m is described by y equals ut plus half gt square. Find the force acting on the particle. We know that y equals ut plus half gt square. This is the motion, and this is actually the distance. This is actually the same equation as s equals ut plus half at square. So we know that this is motion, and when we differentiate the distance or the displacement by time, we will get the velocity of the particle, and when we differentiate velocity, we will get acceleration equals d. The force is given by F equals ma equals mg. Thus, the equation describes the motion of a particle under acceleration due to gravity, and y is the position y coordinate in the direction of g. And now let's go to the next topic here, which is impulse. Impulse. We sometimes encounter examples where large force acts at a very short duration, producing a finite change in momentum of the body. Basically, we see that there is examples where a large amount of force acts on a body during a very short time, and this will bring a finite change in momentum of the body. This is basically, we know that force equals dp by dt, and force times dt equals dp. This is what they're saying here. And force times dt, which is basically the force acting at a very short duration, is what we call it as impulse. Okay. Encounter examples where a large force acts for a very short duration, producing a finite change in momentum of the body. For example, when a ball hits a wall and bounces back, the force on the ball by the wall acts for a very short time when the two are in contact, yet the force is large enough to reverse the momentum of the ball. Basically, if you ever wonder, when you throw the ball, when you throw a cricket ball or any kind of a tennis ball, let's assume, when you throw it with all your power, rotating the hand with full speed, it hits the wall, but it hits the wall like when you're throwing it, you throw it for like about 5 or 6 seconds, let's assume. But when the ball hits the wall, like it is hitting the wall, but if you see the contact time between the ball and the wall, it is only 1 second or a fraction of a second. The it's only a fraction of a second, but when the ball is an elastic ball, you see that almost all the force you applied will be returned back. that is in an instant. The time it took for you to give that force to the ball was 5 to 6 seconds, but the wall gave the same force to the ball in a fraction of a second. This is what we call as an impulse, giving a large amounts of force in a short amount of time to induce a great change in momentum. Let's read the statement again. We sometimes encounter examples where a finite change in momentum of the body. Wait. The force acts for a very short duration, producing a finite change in momentum of the body. For example, when a ball hits a wall and bounces back, the force on the ball by the wall, saying ball and wall is kind of hard, but let's continue anyways. The force on the ball by the wall acts for a very short time when the two are in contact, yet the force is large enough to reverse the momentum of the ball. Often in this kind of situation, the force and the time duration are difficult to ascertain separately. Basically, it's not like you can actually calculate the force, the amount of force you put in your hand to throw the ball, and you can't exactly calculate how much time you can calculate, but it's kind of hard. However, the product of force and time, which is a change in momentum of the body, remains a measurable quantity. Basically, the change in momentum or the product of force and time, which is which is change in momentum of the body, this remains measurable. And this product of force times change in time is what we call as an impulse. Impulse equals force into time duration, or equals change in momentum. A large force acting for a short time to produce a finite change in momentum is called as an impulsive force. In the history of science, impulsive forces were put in a conceptually different category from ordinary forces. Newtonian mechanics has no such distinction. Impulsive forces like any other force is like any other force, except that it is large and acts for a short time. Basically, in before time, they were not putting a consistent slow force when we continue to pull or push a shopping cart. That force, that kind of force, and these when we hit a volleyball, when the ball is coming and we smash the volleyball, this kind of force where we instantaneously apply the momentum or apply a force on the volleyball, and when we continues to pull or push the shopping cart, these kind of two forces in the ancient times or before complete modern science was brought, we can't say it's modern, but fine. In the ancient time, they used to separate these two forces into two distinct categories. But now, in a Newtonian mechanics, we have no such distinction. Both the forces are same kind of forces only. When we are smashing the volleyball or pushing a trolley, both are same kind of forces. It is just that in case of a volleyball, we apply the force instantaneously, but in case of a trolley, we continuously push the ball, and not the ball but the trolley. Now let's see. A batsman hits back a ball straight in the direction of the bowler without changing its initial speed of 12 meter per second. If the mass of the ball is 0.15 kg, determine the impulse imparted on the ball. Assume linear motion of the ball. Change in momentum equals 0.15 times 12, which is the initial speed of the ball, minus of 0.15 times 12. We took minus 0.15. It is not the mass is minus, it is the velocity is minus because it's a vector. And we will get that It is 3.6 Newton per second. When we finally calculate this, basically they are calculating, we do not know the change in time. So actually impulse is delta P or force times delta T. We can use both these formula to calculate impulse, but force times delta T, we do not know the force acting on the body, we do not know the time, the change in time interval. So this is not the formula we go to this formula, because they gave us the mass of the ball, they also gave us the velocity of the ball. So this is the go-to formula, and using that we find the change in momentum, the initial minus, I mean the final minus initial momentum, which is basically nothing but the impulse. Impulse is 3.6 Newton second. It's not Newton per second, but Newton second. In the direction from the batsman to the bowler. Impulse is acting from the direction of the batsman to the bowler. I will be back in a minute. I will be taking a 10 to 15-minute break. See you after the break.